Okay, so this next set of examples, we want to talk about beam deflection. And so the leading paragraph here talks about a lot of different qualities about beam deflection, but let's just kind of graph out what that looks like. And I'm sure you can find much better drawings if you look them up online and that sort of thing, but you're going to get stuck with this. So we're basically talking about two sorts of examples here in our chapter. Is one, we have a cantilever beam, and that's where it's attached to a rigid object like the wall or something there on the end, and the outside is free to move under force. And so we've done some examples like this in the past. But yeah, that would be the thing you see there where it has a length of L. We start with 0 being here at the hard side of the wall, and L being out here at the end of it. We kind of put it on an XY axis. So yeah, X goes its way from 0 to L, and Y deals with, as we talked about down here, the deflection, how much the bin moves when it's put under a force. We'll talk more about that in just a second. The other type of beam we have are simply supported beams, and that's where they have two supports on each end. Again, we'll set the axis at one end of the beam at 0, and the other one will finish at L in our X direction, and Y will be the deflection within the beam. And so what we're talking about here in general is if we put them under the stress of a single load, P, measured in newtons, and for cantilever beams, that's often put at the end, although theoretically you could put it anywhere in there, and it would just kind of change some of the parameters of our equations. But if we push the beam at the end there, or in the case of a simply supported beam, you push in the middle and you get kind of this deflection of things going down in the middle, almost like a smiley face. We want to relate that to a distributed load, one that would be related out over the entire surface of the beam, instead of just thinking of it as, okay, what's the load on the end of the beam that's causing this? What would be the load over the whole thing that would cause the same sort of deflection? And these can be a constant, so that the load is constant all the way across the machine, or you may end up in a situation where, or say machine across the beam, or you may end up in a situation where the load is a function in that it changes as we go down the beam, that it's maybe higher at one end, or it could even follow something strange like a sinusoid curve or something like that. But it has some sort of deflection there. So these quantities that we're trying to relate are, we talked about Y being the deflection, so that's how much the beam is moved, and it's Y of X, so at any given point. So obviously, in the case of the cantilever beam, where it's being pushed out here, the maximum deflection is going to be out here at the end, but it's going to deflect a little bit here all along the way, depending on some different things. Similarly, with the simply supported beam, if it's supported on both ends and the force is in the middle, well, then we'd expect that the maximum deflection is going to be where the force is, or at least close to there, but it still deflects a little bit all along the way. So we measure that deflection, the change in Y, in meters. So then the slope of that would be if we took the derivative with respect to X, and we're used to that, right? If we have a function, whether it looks like this or it looks like that, the derivative of that function with respect to X is called the slope. And so we get this slope, they call it theta, which is a little bit strange for a value. We're used to it being just like m or something when we use a line, but we're going to use theta, and it's measured in radians. So in other words, because it has values of, because dy is going to have meters, and that's going to be per meters, the units are going to cancel out. We'll end up with nothing there. So we can get that slope. If we keep going, there's something in dealing with in the forces with these beams, and it's called the moment. And the moment is found by taking the second derivative of our deflection, and so and multiplying it by this flexural rigidity property. So EI are going to be constant for whatever our beam is, and it depends on what's the shape of the beam and what are the properties of the metal or whatever our beam is made out of. And so EI has units of newtons per meter squared. So while our derivative, if we took it again, we had meters per meter, got us there. We take the derivative again, so it would be per meters. Since this has units of newtons times meters squared, when we multiply those together, our moment actually has values of newtons times meter. We keep going from moment, and we can get to the idea of shear force by taking the derivative again. So we take the derivative again. We're now on the third derivative of our deflection. And of course, since we've taken it with respect to x again, we're dividing out by meters again. So now we go from newtons times meters back down to newtons. And then if we do it again, we get Q, which is our distributed load, they call it, which has units of newtons per meter. So that's one way that we can kind of relate this deflection down to a distributed load. And it goes through a lot of processes to get there, of which you can see it actually ends up taking down to a fourth derivative. So you can guess that for the examples coming up on the next video that we will have to do some of this taking derivative after derivative after derivative.